Hello everyone. So I'll talk about open quantum field theory and its application to 5-4 theory. So this is a work which I have done with Avinash Buddha, who is a student at IISc, with Ilovanagam, and with Arnav Rudra, who is a postdoc at UC Davis. So first I'll introduce what do we mean by open quantum field theory, then what are the motivations of taking this problem, and then I'll discuss how do we do open quantum field theory, and then we'll go on to specific examples like open 5-4 theory, and I'll end my talk with a few open questions. Okay. So what do we mean by open quantum field theory? So let's start with, say, we have two fields in a system. One is system field and one is environment field. And if we integrate out the system, the environment field, let's say this is the whole system, and this is the system, and this is environment. Then if we integrate out the environment degrees of freedom, then we get an effective field theory, and that we call open quantum field theory. And these theories are not unitary. Okay. So the motivations of doing this is to understand dissipation is quantum field theory, because we know that most of the systems we find in nature are dissipative. And specifically, we want to study this problem because we know that exterior of a black hole is can be mapped to open quantum field theory, and that might resolve some issues with black hole physics. So these are the questions we wanted to answer in this paper. So we studied a single scalar field theory, so 5-4 theory, and these are the questions: whether the theory is renormalizable or not, and there are few conditions. So these are constraints on the coupling constants which appear in the action. And these conditions are, we call Lindblad condition, and these conditions, so we check that these conditions, whether these are not preserved at the loop level. And why is this question important, this Lindblad condition? So it is because if these are violated at loop level, so that changes the character of the theory. So that's why this question is important. So this I'll explain more later. Okay. So how do we do open quantum field theory? Let's say we start with a system. Even if we start with a pure state, so after tracing out the environment, we may not end with the pure state. We may end with some mixed state. So that's why we need path integral evolution of the density matrix. And that is given by this equation. And here U can be interpreted as the forward time evolution, and U dagger as the backward time evolution. So let's say this is the forward time evolution and this is the backward time evolution. And that's why we need two fields. So one field that is flowing in the forward time direction, and so that we call the Kate field phi r, and the other field that is flowing through the along the backward time contour, and that we call the bra field phi l. And the path integral is given by d of phi r, d of phi l, and this. And we see that effectively we get an action that we call Schwinger-Keldysh action, and that is given by phi s of phi r minus s of phi l. And one may naively guess that these two fields, phi r and phi l, these are independent, but that is not quite true. It's because these fields are identified at time t equals to infinity. Okay. So these are the propagators which one can calculate in scalar field theory. And these propagators are, since because of this contour, let's say we choose 2 times T1 and T2. So we can place the operators these 2 points, then we'll get phi r propagator. And if we place here, then we'll get phi L propagator. And we can also place here and here and here and here. So that's why we get 4 propagators. And we these left, right, plus and minus propagators. So this oh, I'm sorry, that would be just delta. So this is the usual Feynman propagator, and that is the right propagator. The left propagator is the complex conjugate of the right propagator. So this is this propagator. And this plus and minus propagator are similar to the cut propagators, which we come across in cutting rules to prove unitarity. These propagators, these are related via this identity, which we come across in complex analysis course. That is, yeah, okay. And yeah, so this would be delta only. So far, we haven't talked about anything on openness of this theory. So this is just unitary theory, unitary evolution of the density matrix. Now we'll come to non-unitarity. Okay. So to get that, let's say the environment field is chi and the system field is phi. Then the path integral is given by this. So this is the unitary Schwinger-Keldysh path integral for the density matrix with 2 fields, phi and chi. Now we integrate out the chi field, then effectively we get this action. That is S of phi r, functional of phi r minus S of phi l, and there is additional piece. So these 2 terms we see in unitary evolution, and there is this additional term which has this kind of form. Actually, there are mixed vertex like phi r squared, phi l squared, plus phi r cube, phi l. So this kind of mixed vertex are there. So one can guess that that these are responsible for breaking of unitarity. And this we call Feynman-Vernon influence functional. Okay. Now we'll go back to open quantum mechanics. So if we impose these conditions, yeah.
Your original phi chi theory was some purely unitary.
Right. Yeah.
And why, when you integrate out chi, why do you see breaking unitary?
Oh, what? Sorry.
What is that? What is that?
Sorry. Okay.
It's not like integrating on a massive field. That we don't normally call that.
Yeah. Okay. In unitary theory, there we don't see any mixed vertex like phi r squared, phi l squared, and these appear because of let's say at the loop level we have this diagram. Let's say we have this diagram, and this come from this is the P propagator, this is the P propagator. Okay, now if we integrate out this field, this comes from the environment field, then we get this kind of vertex.
Right, so you've also got non-locality within any given point.
Right, yeah.
Right.
So that's how we get this functional. Shall I move on? Now we go back to open quantum mechanics, and if we impose these conditions, that is trace of rho here, the density matrix of the subsystem, and that to be 1, and also the eigenvalues of rho are positive, that comes from the physicality condition. And then we impose one more constraint, that is Markovian approximation. Then the time evolution of density matrix is given by this. And here we see that this term, that is commutator of H and rho, this comes from the unitary evolution, and the rest come from the non-unitarity. So here gamma, alpha, beta, and there will be a comma here, alpha, beta. Okay. So gamma, alpha, beta are coupling constants. This L alpha, L beta, so these are called Lindblad operators. Now if we go to the field theoretic picture, then we need to go to Heisenberg picture, because this is in Schrodinger picture. So in Heisenberg picture, time evolution of any operator, that is given by this. And from here we can directly write the Feynman-Vernon influence functional from this part. Okay. If we write the form, then is and so here this L alpha dagger, this is a function of phi r. So this is because this comes from L alpha dagger, and that comes to the left side of A, and that belongs to the forward time contour of forward time contour. That's why it's a function of phi r, and this is a function of phi l because it comes from the backward time evolution. Okay. So to summarize, so what we have done, so how do we construct action of an open quantum field theory? So first we write a Lagrangian that come from unitary Lagrangian, unitary theory, so L of phi. Then we double the field, that is minus L of phi L, and say this is phi r. Then we add all possible terms with mixed vertex, that is all possible Feynman-Vernon influence functionals. So that's how we construct the action of open quantum field theory.
Why do they come with the specific coefficients and signs?
Yeah, okay, we can directly see from this. That is, there is a minus, so that's why it's minus. And so this L alpha dagger, L beta, so this comes at the left side of A, so that should be a function of phi r. Okay. Now we come to specific example, that is the application of this formulation in phi theory. So here the first three terms in the first line, that is the usual phi-4 Lagrangian. And the second three terms in the second line, that comes by doubling the fields, and the rest of the terms comes from the Feynman-Vernon influence function. And you see that so all the other terms, so these these have mixed vertices, that is phi r cube, phi l cube, phi r, mixed vertices. And this action is CPT invariant. So under CPT, phi r goes to phi l and phi l goes to phi r. No, we won't look at the environment field. We can directly construct action.
A normalizable form of it.
Right, yeah. Yes. Actually, we can construct from this the microscopic theory.
Lambda and lambda star are complex, or they are just real?
Yeah, these are complex. And here Z delta, M delta square, and delta, these are real numbers. These come from CPT. So if we impose CPT, this has to be real. So now, if we write this Lagrangian in this form, I mean this form, the Lindblad form, then we get few constraints on the coupling constants, and these are the following constants.
Lambda star complex functions, where does that come from?
If we don't, then it will be just a unitary theory. Because if it is complex, then there is an imaginary part, and then there is a decaying factor. Okay, sorry. Lambda 1, lambda 2.
Coefficient phi r to the 4.
Yeah.
Complex quantity with coefficient phi n.
Right.
Why does that? Why is that?
Yes, yes, yes. Because of CPT, this has to be true. But okay. Yeah. So we get these constraints, and so in the beginning we yeah. Yes.
You said under CPT, phi r and phi r getting changed.
Yes.
Invariant, then lambda should go to minus.
Lambda go, no. Actually, I times x is invariant. Okay. So the first question was the theory is renormalizable or not. So actually, the theory is renormalizable. That means the divergences which appear at the loop level, so those can be absorbed via counter terms. And the other question. Okay, so these are the beta functions for all the coupling constants. So these relations are may not seem so interesting, but if we look at the beta functions of the coupling of the Lindblad conditions, that is these are the Lindblad conditions, then those beta functions are proportional to Lindblad conditions itself. So that means that if we impose these conditions to be zero at the tree level, so that those remain zero at one loop level also. And this imaginary z minus z delta beta function for this is identically zero, because we know that in phi-4 theory at one loop there is no field renormalization.
Divergences in cross terms. Could you go back to Lagrangian one?
Sorry, I didn't understand.
Can you go back to Lagrangian?
Okay, yeah.
So now you have, for instance, this delta, phi r squared, phi l squared, then r and l are the top and bottom. Is this right?
Right.
Or, yeah. So,
Yes.
So this is the term that would not be there on the end.
Right, yeah.
And that also, delta picks up a divergence. There's a beta function for delta as well.
Yes, yes.
Next slide. Is that obvious that these are the?
Yes. So so if we write that Lagrangian in this form,
Okay.
then we'll get this constant. Yes. Okay. So we also have a diagrammatic proof that these conditions are never violated at all order in perturbation theory. So why is this important? It's because if these were not zero under renormalization, then the theory is not Markovian. So that's why this was important. Okay. So I'll conclude with a few open questions. So we have tried with two scalar theory, that is with say 2 phi-4 scalars in the theory. Then the theory seems not to be renormalizable. That is, there are non-local divergences of this kind, 1 over k squared, 1 by d minus 4. So this kind of divergences are there. And one can also extend this idea to fermions and then QED. And one more interesting question is, so starting from some unitary theory, so can we directly get a macroscopic theory and study how the unitarity is broken? Is there any mapping? So that is one important question. Okay, thank you.
Questions?
There's some kind of hidden supersymmetry in this theory.
I don't know.
Just to follow up on the last point.
Yes.
What I understood is that you showed that if you start with this renormalizable form of the action, and this Lindblad condition is maintained at the beginning, it'll be stable under renormalization. Now, what if you did what you were talking about at the beginning, that you had two fields,
Yes.
you integrated one out, and you get an effective action for the second field? Will that automatically satisfy this Lindblad condition?
I think so, because
That's easy to say. Actually, maybe you can also say, what is Markovian? What does Markovian mean?
so here, that is in quantum mechanics, but here it's locality. So in quantum mechanics, Markovian means that, say rho of t, okay, say this is epsilon of t naught, that's rho of t naught. So this was the time evaluation of density matrix, let's say. So in Markovian approximation, this becomes t minus t naught.
What I'm trying to understand is this Lindblad condition, is it supposed to be some exact statement about quantum field theory? If so, we should be able to prove it, right?
Yes.
I want to understand the status. Is it an approximation? Is it some reasonable condition? Is it something you expect to be true of any?
Yeah, this is, I think this is an approximation that theory is local.
So, but I think that this is simply coming from the fact that you take unitary evolution. So you have a Hamiltonian, it has this field phi, it has this field chi, and then you integrate out chi. That'll give you some density, so if you now look at the density matrix for phi, you'll just get a Lindblad equation for that. So I think that's exact, right? That should hold in quantum field theory as it does in quantum mechanics. It's simply the statement that, unitary evolution of the full density matrix was evolving unitarily. You traced out some part. So the smaller density matrix now evolves with this, with some other super operator evolution, and that super operator obeys the Lindblad condition. So I think it should be exact. But
And you can prove that from?
maybe it's better to.
Cutting rules of the microscopic theory, if you, with phi is outside, and if you demand that the microscopic theory obey cutting rules, the theory with phi and chi obey cutting rules, and then the diagram which contribute to these couplings, then you integrate it out.
So microscopic theory obeys the cutting rule, including phi and chi.
Yes.
Now you know the chi does, you get some condition of the phi.
Yeah. So when you integrate out chi, the couplings that you produce should be consistent with the fact that
If you put chi back in,
it should be united. So,
that condition is something that will be done in the phi.
But you don't need diagrammatics, right? You can do this at the level of Hamiltonian evolution. There's a Hamiltonian.
Diagrammatics also.
Yes, you can do it at the level of diagrammat, but the Hamiltonian evolution itself will tell you that the Lindblad condition holds for the phi field.
Yes. The trace rule should be what.
Just imagining that to give you that.
Yeah, there are many ways of getting the same problem.
So then if you take out the chi field, from what you said, it's obvious that the condition. From what you said, it's obvious that you don't have nothing.
But now I'm puzzled about why you said it doesn't. There's some problem with two fields. That's very puzzling. You said if you have two scalar fields and you write down the most general renormalizable interaction, if I understood correctly in the last statement, you said that there is non-local divergence.
Yeah.
What happens with two scalar fields that doesn't happen with one?
Let's say we have a diagram with, let's say we have this kind of loop.
First statement is there's no problem in the Lindblad condition. It's a question of renormalization.
Yeah. So Lindblad condition is always true.
Problem of renormalization. You can't add local counter terms for some reason. I'm very confused about. Yeah, what happens with two scalar fields?
So we have this kind of loop. And the divergence is of the form m phi squared minus m chi squared by k squared 1 by d minus 4. So if m chi equals to m phi, then sorry. Actually, I forgot, but if m chi equals to m phi, then 1 by k squared is cancelled. I guess this form m squared plus, I guess it's of this form m phi squared plus m squared chi squared. If m chi, no, not this also. I forgot. Oh. So in the m phi equals to m chi limit, these divergences are cancelled.
Physically, what's the difference between one field and two fields? You're saying, so can I ask, you're saying the most general renormalizable action that you had, you can't get it by integrating out. If you could get it explicitly by integrating out some chi field, then that would be, then you would be done, right?
We have not resolved it. Yeah, we do not know the answer to it.
But if these two fields have some symmetry or some O2 symmetry or something, then it's okay.
No.
Then it's okay, right?
Oh, then it is okay. Yeah, yeah.